So in the previous lecture we talked about lambda calculus and lambda functions briefly, just scratched the surface. And we saw that lambda calculus forms is an alternative to mathematical logic. It's a logical system. Today we're going to talk about type theory and type systems. And then we'll see that type theory is also a mathematical formal system, which again provides an alternative formulation of set theory. Now, both logic and set theory are absolutely foundational to mathematics. So you can imagine that these things go very, very, very deep, and we are absolutely not going to go there. So we're just going to talk about these things very briefly and see how they can be useful to us as programmers. And the whole motivation for type theory actually arose because lambda calculus turned out to be a little bit too powerful. You could actually end up expressing mathematical paradoxes in plain untyped lambda calculus. So Church invented the typed version of lambda calculus, which put some restrictions on what the terms could be. And this gets very close to what we need as programmers to tell our programs what valid inputs are. So for example, we can, just to make things a little bit more concrete, we looked yesterday at how we could define a pair in terms of lambda calculus. And that was just simply lambda x, y, f, f, x, y. Which achieves a pair by partially applying first one value which gets stored in a closure for x, then another for y, and then finally it accepts this last thing here, which is something that will project out either of these two values. Now if you look at it like this, there is absolutely no restriction on what x, y, and f can be. And now we can think a little bit about types and see how they are related to sets. So if we look at a pair can be a pair of whatever. So that means that this x here is the set of anything. Like this is the set of whatever. The set of all values. And the same goes for y. Now f. What about f? Can f be anything? Well, if we look at how this is used, then suppose now we would say that, well, f is 5. Then this thing here would be completely meaningless. Since you cannot apply 5 to two different sets. It doesn't give any kind of, it's just nonsense. So f cannot be anything. Then we need to put some restrictions on f. And we'll see that we need to put some pretty hefty restrictions on f really. So if we call this, we can say that, well, this x here belongs to the set which we call A, and this y belongs to the set called B. Now this f here needs to belong to something which contains the set of things that have the structure, something which takes an A and a B to produce, what should it produce? Well, it needs to produce either an A or an B, right? This would be absolutely nonsensical if this would produce. So suppose I would put in say that A is the set of ints and B is the set of floats, and I would put in 1, 2, 0, and then I would pick out some stuff from this pair, and it would say foo, string. That wouldn't make sense, right? So it needs to, this f needs to either give out an int or a float. So these are the restrictions that we have for this pair, for this thing to make sense at all. And now we see that how these types and type theory starts restricting what we have. And this is what we're going to be using a lot, and we're going to see how useful it is. And I'm pretty sure most of you are familiar with types in computer languages, because many languages have them. But so there's some deep connections here, and we're just not going to go there. But I'm just going to mention them very briefly, because it sort of shows you how big and mind-bending this actually can become. If one does category theory, there is a connection between type theory and lambda calculus in category theory through something called Cartesian closed categories, which again are very closely related to what functions are. So there's all these connections behind the scenes that one can find if one is interested in these things. Another interesting thing that we can find is that there is a very famous theorem, or it's called the Curry-Howard isomorphism or correspondence. Some people like to include a guy called Lambeck as well. We can probably tack on a few more names there, but and this states something very interesting. It states that there exists a mathematical isomorphism. This is not some kind of like-ish, that there is a very strict, real isomorphism between types and theorems and lambda calculus and proofs. In fact, this is something that can be utilized and is utilized a lot. So there are things called mathematical proof assistants, which are special kinds of computer languages which implement type theory really to the extreme, which allow mathematicians and computer scientists to prove theorems with the help of computers. So they are helping mathematicians prove theorems. This is how far it goes when one takes this type specification to its extreme. You can really express down to the latest most minute little detail of what is valid inputs to things. You could imagine things like having a lambda function where you have some function and you say that this thing here is restricted to only accept primes. It's only valid for primes. That's not an uncommon, an unreasonable restriction in mathematics. As programmers, we probably would say, well, oh, that's weird. How would you do that? Try to think about how could you do that in your language. This can be done with a proper type system. So this is a little bit of sort of the background for this, but of course we are not going to concern ourselves with proof assistants and the like. If you're interested in this topic, you can go out and check out languages like Coq and Agda. They are two kind of popular proof assistants out there. Neither of which can actually produce runnable code, but the point of them is the type system rather than the implementation. I should mention that there are languages like Idris and F star and a bunch of others which do implement type systems. These are called dependent type systems and linear type systems, where you can go a fairly long way in this proof idea, up to the point where Microsoft, who is behind F star, have an initiative where they are re-implementing the whole SSL base libraries for encryption in F star, where they will prove the correctness of the library rather than test it. I guess this is a statement that was sort of not exactly precisely correct, but almost. But that's the basic idea, where you can actually wire down the specification of your problem to the point where you can be sure that you do not have any bugs because you have proved it. That's how far you can go with these things. And that's not us. We're just going to go halfway, if even that. Right. So that was types and the sort of essence of types. Now, type theory can then be used to define type systems and type checkers for computer programs. And most of you are probably familiar with in languages like C, where you can say that something is an int or a float or an unsigned int, or it's a record structure or a union or something. And that's basically, and it sort of ends there. You go to C++ or C# and Java, you get polymorphic types, which are already a good deal more advanced things. In F#, we go a bit further. If we go to Haskell, we go still a bit further with these things. But the whole point of having a type system in the end, really, is to put some rules on how we can use things so that they can forbid us from doing the wrong thing. Which means essentially forbidding us from writing invalid programs. But on the other hand, a type system shouldn't be so strict that it forbids us from writing valid programs. So there's a balance always in practice how we do things. But like if we take some example like JavaScript, which is notorious. So if we do in JavaScript type empty object, just object, nothing else, just empty object, and we add a empty array to it, what should we get? In my opinion, we should get a type error. These two, but you could somehow think that, well, an array is an object, but then you have a different type of object with another object, and we don't really know. In JavaScript, this is 0. Yes. Oh, sorry. So what if we subtract an object from an object? Well, this one is actually correct because it's not a number. Good going. So this is the idea of type systems, to get rid of that kind of absolute nonsense. But one of the problems that we encounter when we start putting types on things, and I think many people who have used type systems have realized that they make it harder to code. And type systems come in the way of actual expressing what we want. And we know that it's right, but the type system says no. So type systems, the more advanced your type system gets, the harder it gets to use. So if you try to go and learn Coq and Agda, you're going to need to spend a lot of time to get acquainted with how those things work. And you're going to struggle a lot with those type systems in order to be able to express precisely what you want. Now, if you've ever done mathematics and done proofs and theorems in math, you know that is hard stuff. So, same thing here. So what we really want in our computer language is to have something that strikes a nice balance between giving us a lot of expressive power, being easy to use, and fast to execute. And when I say fast to execute compile time. Static type checking happens compile time. It doesn't affect the runtime of our code. Not the type checking, at least. It can affect the execution speed of the code, but most often in a good way. So So in our language, if we look at type systems, also we know that programming languages like Python and Clojure and so on, they don't really have any types. They have some of these have tacked them on a little bit, but there are no types. But that's not really correct. They have one type, which is correct for everything. And so there's no compile time checking of types. But there certainly is a type checker checking that when everything has been resolved, that you know that integers are integers and floats, and that you're not mixing apples and pears. And if you do try to add 1 to a string, then it blows up and you get an exception at runtime. And that's a bad situation if that was in the code that controls some rocket on its way to Mars. So you rather have your compiler tell you that that thing is going to blow up in that situation because you are not given a full and complete specification of the problem at compile time. But it's cool because you can do things in Python. You can do say, well, if x equals y, then, well, you don't write then, I guess, then 42, else string foo. Completely valid. But now the type that is returned by this thing, of course, is the set of anything. So whereas in the F# world, this would be most illegal. You need to return one type, and it needs to be defined beforehand, which is a little bit restrictive, but it's a good thing. So type checkers. So if we like we can write down the pair function in F#. Fun x y f, and this should be a to b to c. I'm going to write c here because I can't. I need to pick one or the other. So that's so this is c here is actually a or b. So what does the type checker do when it encounters something like this? Well, it needs to check, when you are using this function, it needs to check that all of these things match up. And now I have these generic things in here which I haven't said anything, which makes things much more complicated. And the way this works is essentially that there are a whole set of rules in the type checker called judgments, and it will check every term against those, also the result here, what this produces. It will check those against the judgments, and it will say, okay, fail, 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 fail. Judgment fulfilled. True, true, true. And then we can say, well, and all of this should return a C, which is the same as that. And then when everything evaluates true, the type checker says this thing here is a type-wise is a true statement, and it's okay, good to go. So which means that when I actually call this thing here with an int and an int, it will say that okay, that has to be an int, and if that's an int, and if that's an int, everything is good. We're good to go. And then we can compile the body because then we know that everything is matching up. So this is basically how type checkers operate. They are checking hundreds of judgments against all these things to figure out what's going on, and to just make sure that everything is kosher. And in functional programming, there are a whole bunch of type systems. One famous one is called System F, which sort of forms the basis of what is used in F# and Haskell, and then they build on this and add and subtract. But this is one of the things that if you want to go and check and learn more about type systems and type checking, then looking up system F can be a daunting thing to do. Now, for anybody who has used C# and C or C++, they know that types are tedious. You have to type, everything has to have a type, because if you don't give a type to something, then we don't really know what the type is, and then the type checker can't do its job. So we end up typing and typing and typing and typing and typing a lot. But in slightly more powerful type systems like system F, they actually are designed very, very carefully so that they can be run backwards. So instead of checking that everything is okay in order to see that things match up, they can look at the result of something and say, well, okay, this produces an int. So if I make some function here, let's say lambda x y equals x plus y, then the type checker would see this thing here and it would say, oh, I know what this thing is. That's an int. That's a function taking an int and an int and returning an int. So then it says, aha, now I can infer that x must be int and y can be int, because otherwise this will be false. So I know then by just looking at this, I can go backwards and say, well, then these things must be int. And now when you try to call this thing here with 4.0 and foo, it will fail, because it will know that that's a float and that's a string, because it has inferred things. And this is a very powerful and nice thing in type systems that we have in F# and Haskell and Idris and so on. We can write them almost like dynamic languages, and the compiler will figure out what the types is for us. And sometimes it needs a little bit of help, a little nudge and a little push, but most of the time it figures it out really nicely and smoothly, and we don't have to bother with type specifications explicitly. Although it's useful to have them, so good IDEs like Visual Studio Code and Visual Studio and the like, they will actually print the type that has been inferred, but which is actually not written out by us, which is a nice, really nice feature to have. So, benefits of having a type system. Well, one, it detects errors at compile time. So we don't really have to run the code and then it's been running for 2 weeks and then it blows up. That's sad. Another really great benefit, which we will talk about in the next lecture, which will talk about types in F# in more detail, is something called ADT, algebraic data types, which actually provides us with a simple programming language of logic in our type system. So we get the language of and or and not and so on in the type system. And that allows us to actually encode a lot of the sort of business logic already in the type system. So what we can do, instead of writing code, we can just sit down and we can do large parts of the sort of design of the system just in terms of types. We are writing down all the theorems for how our program should work, and then we'll just fill in the proofs, which is the implementation. We'll see during this course how types actually act as very good documentation, because we know that types need to match up. So that means that you can just by reading, if you use type systems cleverly, you can actually name types in a smart way, and you don't really have to write any documentation. The code becomes easy to read, it becomes easy to use, and you can just follow the types and pull things through. In a language like Haskell, they have a search engine called Google. So if you don't know the name of the function you need, but you know exactly that, okay, it needs to take an int and a string and produce a list, then you can search for something taking an int and a string and produces a list. And it will go through all the Haskell libraries and it will find you all those functions and try to rank them for you. And then you can say, here's something that seems to be what it is. And you put it in and usually it works. And that's amazing. And this leads us, all of these things leads us to something called TDD, which is not test-driven development, but type-driven development, where we basically design our programs from the types and the data structures and how they should look, and then we fill in the code. And this is a very powerful technique that we will try to use in this course as much as possible. And the final usefulness of types is really, I sort of alluded to this, is that the more the compiler knows, the more precise information the compiler has about your problem specification, the better it can optimize it. Like you can write up, the more information the optimizer has, the better it can optimize this. And I can't remember from the top of my head, there was an example from Idris, which has a very powerful type system, where he basically, the author of Idris, had tested some algorithm, and he specified the types and very carefully, and he ran the code, and it was faster than the fastest C implementation up there. To his great surprise, because he hadn't really optimized the compiler very much. It was just that it had so much information about the problem already. It was a bit of a lucky break, I guess, but it sort of shows a little bit of what's possible for anybody who is interested in language design and things like this. And of course, a great example of this is Rust, which has a more enormously powerful type system. It's sort of slightly more powerful, I think, than F#. It's somewhere between F# and Haskell in terms of power, the Rust type system. And the speed of the code coming out of Rust is just blazing. So that's a great example. Before we conclude, I just want to mention there's a paper for those who are interested in seeing how far you can push these things. And this is not going to the extreme yet in any way, but there's a paper, I'll try to put up the link. His name is Thomas Hallgren, and he's using Haskell, and he implements multiplication, addition, insertion sort in the type system compile time. So he can solve these problems. So he can add numbers and he can multiply numbers and he can sort things in the type system at compile time. So that's how far you can take type theory in without even going to the extreme. So this gives us an expressiveness in this area, which I think, coming from a traditional programming background, you're not used to this. And this is also one of the sort of, I think, problems when learning functional programming, is that you typically, if you go for a language like F# or even Haskell worse, is that you're not just learning functional programming and how to use functions efficiently. You also need at the same time to learn how to use types efficiently, and this can be a bit overwhelming. But we'll try to take this easy, in small steps, and it's going to be all fine. So, that was all for now. Next lecture will be on types in F# and algebraic data types.